Hi, folks. Okay, so let's take a look at the first section in this unit. What's really in the ocean? So, all water is not created equal. Okay, fresh water is water that we drink, it doesn't have any salt in it. Then there's seawater, contains salt and other salts. So, it's not just like the table salt that you're familiar with, but it's also other kinds of salt. And it has those salts are 3.5% of mineral substances. Then there's metals and other kinds of dissolved gases like CO2. Okay. The total amount of solid material dissolved in water is called salinity. Okay. It's a ratio of mass of dissolved substances to water. Now, because the proportion of dissolved substances is such a small number, oceanographers express salinity in parts per thousand. So that uses the little symbol that I have right here, which is the percent with an extra little zero on there, and that represents parts per thousand. So when you see that, it's not a percent, it's parts per thousand. Now, the average salinity of seawater is about 3.5%, okay, or 35 parts per thousand. Now, most of the salt in seawater is sodium chloride, aka common table salt. This is the kind of salt that you have on your dinner table. Now, dissolved substances in the ocean come from the chemical weathering of rocks and Earth's interior. So basically, like those rocks that are formed when rain hits them, or you have any other kind of erosion, salts from there and all kinds of metal and stuff, they end up in the ocean. Runoff from rivers and streams brings about 2.3 billion metric tons or more of materials to the ocean each year, and volcanic eruptions, water vapor, other kinds of gases that were emitted into the atmosphere over the last 4 billion years were then condensed into water when the oceans formed. And that's how some of that stuff got into our oceans. Now, the relative concentrations are constant everywhere in the ocean. That means, anywhere in the ocean, if you took a measurement of the salinity, you would basically have the same amount or around the same amount. So 33 to 38 parts per thousand. Okay. It doesn't matter where you are, it's the same. Okay. Now, the amount of water, however, can affect the salinity. Like if you have some salt water and some fresh water, that can change then how saline that water is. Like if you have more fresh water, then you actually have a lower salinity, okay? Because fresh water doesn't have any salt in it, so that would lower how much salt content is in the water. Things like precipitation, like rain or snow, runoff from land, if icebergs are melting or sea ice is melting, all of those things can affect the salinity. Evaporation and the formation of sea ice can also raise salinity. So that means fresh water evaporating or turning into ice can increase the amount of salt in the ocean. Now, the ocean surface water temperature varies with the amount of solar radiation it gets, depending on where it is, and it's a function of latitude where it is on the planet, right? The polar ice caps have less sunlight, less solar radiation than the tropics. Okay, so if you're in an area where you have low sea temperatures, that's usually in high latitudes because it's colder there. And if you're warmer sea temps or higher sea temps, then you're in the lower latitudes or near the equator. So surface water is warmed by the sun, okay, but deeper waters don't get as much radiation, so they're colder. All right. Now, at 1,000 meters, the temperature is just a few degrees above freezing and stays constant to the ocean floor. Okay. That's 1,000 meters below sea level. Sorry, I should have said that. Okay. So once you get to like 1,000 meters and below, it's just cold and it stays constant all the way to the ocean floor. The thermocline is this region between 300 and 1,000 meters below sea level, where you have this rapid change in temperature with depth. So zero is the surface. About 300 meters down, we start to get this thermocline, and that goes down to about 1,000 meters, and then below that is our deep water region, and that's just just above freezing. Now, because higher latitudes have cold surface waters, there's no rapid change of temperature with the depth. Okay, so in higher altitudes, like polar areas and stuff like that, there's no thermocline. It's just cold all the way through. And the water column is what we call isothermal, or the same temperature. Iso meaning same. Okay. Now, the density. Density is a concept where you take mass and divide by volume. Okay. It's basically how many molecules are crammed into a given space. Like gas is not very dense at all. It has very low density because you've got a lot of molecules spread evenly apart from each other, and they're not super crammed in. High density is like a bunch of people crammed into a subway car. Okay, it's like lots of people, not a lot of room. You're like, shove, 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 because you don't have a lot of space. And that tends to be like solid ice, for example, has very high density. Now, the density in water determines its vertical position in the ocean. Okay, high density sinks, low density rises. So if you think of something like a metal weight and you drop it, it goes all the way to the bottom of the ocean because it's high density. Okay, versus something that's not very dense like gas rises to the top. Okay, now salinity and temperature influence density. Okay, the more saline it is, the more density it has. The more salt it has, more dense it is. If you increase the temperature, basically make it warmer, you lower the density. So warm water rises to the top because it has a lower density. Temperature has more influence because it varies more. Okay, so in most cases, when we're talking about variation in where the water is, we're talking about temperature. Now, density varies in extreme polar areas. So this is where the temperatures are very low, and they stay constant. And so in those areas, because the temperatures are low, the salinity is the thing that determines density in that area. So in those polar ice caps, cold water with a high salinity is the densest water in the world versus temperature and salinity varying with depth, like higher temperatures means low density, that kind of stuff. That's in like near the tropics. Okay. So let's see. The pycnocline. Okay, so the pycnocline is a layer of ocean water between 300 and 1,000 meters where there is a rapid change of density. Okay, so this is basically kind of like that thermocline, right? Except it's not thermo because it's not temperature, it's density related. So we call it a pycnocline. Now, this area prevents high density and low density water from mixing. So it's sort of like a barrier that prevents that kind of water from mixing. It's not available in those higher latitudes, so in the polar areas where the water is the same density throughout. Okay. In the high latitudes, you basically don't have it, but in the low latitudes near the tropics, you've got that. Now, the ocean is layered according to density. Okay, remember low density near the surface, high density below. And except for some shallow inland seas with high evaporation, where there's a lot of evaporation, so there's a lot of salt content, and you've got that high density water, generally, highest density water is found at really deep ocean depths. And there's like a 3-layered structure in our open ocean. Okay, there's a shallow surface, a mixed zone, there's a transition zone, and a deep zone. The surface zone is up here at the top. It's at the ocean surface. You got the warmest water temperatures and all that stuff. Then you have the mixed zone, okay, which is an area of surface water that's created by mixing water through waves, currents, and tides. Okay, sorry, that's this mixed zone right here. Now temps are uniform in this area because you've got a lot of mixing, and this is the 0 to 300 meter range below sea level. Okay, sometimes it goes to like 450 meters max. Now only about 2% of ocean water is right here in this mixed zone. The transition zone is an area that has the thermocline and the pycnocline, okay, the 300 to about 1,000 meters below sea level. Temperature tends to fall with depth, so the closer you get to the ocean floor, like the farther down you go, the colder it gets, and this is about 18% of ocean water. The deep zone is from 1,000 meters below sea level to the bottom of the ocean. No sunlight reaches here, so the water temperature is just above freezing. And you have constant and high density. It's really heavy water, and about 80% of ocean water is located there. Now, there are just over 250,000 species in the ocean, okay, and there are more that they're discovering every day, so that number can be outdated by now. From microscopic bacteria to blue whales, which are the largest organisms alive today, To get an idea of their size, it's like 3 school buses, end to end, all right next to each other, like pretty long. That's how long the blue whale is. Now, most live within the surface waters, okay? They need sunlight because sunlight powers photosynthesis by the marine algae, which is food for other organisms. So they stay where their food is. Now, marine organisms are classified according to where they live and how they move. Plankton are essentially floaters. They're little organisms that drift along with ocean currents. Generally, these are like algae, some animals, and bacteria. Nekton are swimmers. Okay, it's from a Greek word to swim. So some can swim, or sorry, plankton, some can swim very weakly, only move vertically. They're very basic. Uh, Nekton is the swimmers, aka fish, and then benthos are the bottom dwellers, and we'll look at those in a sec. So algae that do photosynthesis are what we call phytoplankton. Okay, the phyto meaning light. All right. Most of these are microscopic. Some examples are called diatoms. They're really small, you can't see them, and that kind of stuff. Animal plankton are plankton that eat phytoplankton, and they're what we call zooplankton. So zooplankton are like, you often see larval stages of fish, sea stars, lobsters, crabs. They're super little, and they're gooey, and yeah, they eat other animals. Nekton are all animals capable of moving independently of ocean currents, okay, either through swimming or any other kind of propulsion. Many do long migrations, and they include adult fish and squid, marine mammals, and marine reptiles. Fish are more abundant near continents, islands, and in colder water, so we tend to see them closer to where humans are. Salmon actually swim upstream in freshwater to spawn. So they mostly live in like salt water, but then they swim upstream freshwater, up rivers and stuff like that to spawn in freshwater and make their babies. And then they swim down back to the ocean to live out their lives. Eel do the opposite. They live in freshwater and they mature there, and then they swim downstream to breed in the ocean, and then they swim back up to the freshwater to mature. So more marine nektons kind of look like this. I'm just giving you a big picture of animals. Here you have the plankton, the nekton, and now we're going to talk about the benthos. The benthos are the organisms that live on or in the ocean bottom. Most of these organisms live in the shallow coastal ocean floor. So this is like near the coast. You see things like seaweed, for example, that are attached to the bottom of the ocean because there's enough sunlight in that area, they can survive. You might see the larger algae, the other kinds of organisms, like a lot of like plants and animals and stuff that eat off of those things. Now, there is a part of the region of the ocean that doesn't receive light. And in that deep ocean, it only has animals because there's no light, so you don't get any photosynthesis. So these organisms live in perpetual darkness, like in the pictures here. The light is being provided by humans, so we could take pictures. So these are some examples of organisms that live in the benthos. So kelp, sea snails, sea anemones, bat stars, these are all in tide pools and stuff. So these are surface dwellers. Um, so 3 factors that are used to divide the ocean into distinct marine life zones. Basically, the 3 conditions are what's the sunlight like, what's the distance from the shore, and the water depth. Okay, so if you see light, if there's light in that region, it's called the photic zone. Okay, this is the upper part of the ocean where sunlight reaches. This can vary, of course, time of day, season, year, latitude, and all kinds of particles that might be in the water blocking sunlight. And then you have the euphotic zone, which is near the surface up to 100 meters below the ocean, and below sea level, where light is strong enough for photosynthesis, but it's not like the surface. Okay, now photosynthesis can't happen below 100 meters below sea level. So in that lower photic zone, we mostly see marine animals, like organisms that can find food, avoid predators, recognize other members of the species, locate mates because there's enough light for them to see. And like the organisms above 100 meters tend to be the plants and the algae and that kind of stuff. So it's like up here you got the photic things, then you've got the lower photic zone where they can still see and they're kind of hanging out and chilling in this euphotic zone. And then we get the aphotic zone, which is below the photic zone, where there's no light at all, and it's basically dark all the time. Now, in terms of distance from the shore, okay, there are several zones that we're going to talk about. So there's the intertidal zone where land and sea meet and they overlap. Okay, this is essentially the shore, the coast, right near our continents. Organisms that live here have adapted to constant environmental changes of tides. So, like, there are certain beaches where you can actually see this intertidal zone because they're what we call tide pools, little sections of land that kind of dip and are formed by rocks and stuff like that. And during high tide, they're covered in water, but during low tide, the water is kind of still because it's like a little pond, of seawater. And you can actually go to low tide and see all the organisms that live in there. It's pretty cool. I have some videos. I went a few years back. So ask me in class and I'll show you them. So the low tide line from that zone, from the area to the continental shelf, which is deeper into the ocean, is what we call the neritic zone. Okay, this can be narrow or extend hundreds of kilometers from the shore. This entire zone is completely photic. There's light there. And this is about 5% of the world ocean, but it has 90% of commercial fisheries. It has so many species there. Because again, sunlight provides food for plants that then can feed animals. Okay, so to give you an idea, here is our intertidal zone right near the coast. Then you've got the continental shelf, which is kind of surfacey, and then it dips. And this continental slope goes to the abyssal zone, which is all the way at the bottom. Now, the oceanic zone is beyond the continental shelf, so that's pretty much continental shelf and all the way into the ocean. Nutrients at this point sink to the ocean floor, so not a lot of animals can live in this area because there's just not the nutrients. Pretty much once you get past the continental shelf, it's like surfing and everything happens before the continental shelf, like closer to the coast. And once you get to the continental shelf, like the only thing out there that, in terms of humans, like you can only survive if you're on a boat, you know. So the water depth is, it's basically like an ocean zone, open ocean of any depth is what we call the pelagic zone. Here we have animals that swim and float freely. They have light and photic and aphotic zones, so light and no light zones. The benthic zone is any sea bottom surface, regardless of its distance from shore. Okay, so any animals that attach to, crawl upon, or burrow in that seafloor are in the benthic zone. Now, the abyssal zone is a subdivision of the benthic zone. Okay, this is like the super deep ocean floor. All right, that's what we call the abyssal plains. And here we have really high water pressure, constant low temperature, no sunlight, sparse life. So, if you actually, to give you an idea, if you watched Aquaman, like DC movie Aquaman, they have a really good, like, kind of CGI sort of fake version of this zone. Atlantis was in the abyssal zone. Okay, it was like super dark, and it was only when like Aquaman's like eyes like activated that he could like see in that area, and that was because like they anyway you can look at superheroes if you want, but the point is that it's super dark down there, high water pressure. Humans really can't survive unless we're in like specialized suits or like submarines and stuff. It's super difficult to live down there. Food comes from the surface or from dead organisms that sink to the floor, so there aren't really like complex organisms down there. Mostly it's like bacteria and other kinds of little things. Now, hydrothermal vents are vents along the ocean ridge where seawater creeps into the ocean floor through cracks in the crust. And at this place, the water becomes superheated and saturated with minerals. And that then seeps back into the ocean. And it creates this black smoke effect that you see in the picture here in the water. And in some of these vents, we actually can find organisms that are not found anywhere else in the world because they're completely and 100% unique. Okay. Now, food always starts with primary productivity. Okay, it's basically organisms that can turn inorganic compounds like nitrogen and carbon and phosphorus and stuff like that into organic compounds using photosynthesis. Okay, basically these are plants. There are also organisms that can do this using chemosynthesis or chemical energy. Okay, so bacteria in these hydrothermal vents use something called hydrogen sulfide as an energy source. And so they can turn those inorganic compounds into energy and into organic compounds. Now, there are two factors that influence a region's photosynthetic productivity. Okay, it's the availability of nutrients and the amount of sunlight. And so we're going to talk about how different regions and different kinds of organisms can operate based on what their limiting reagent is. What do they need in order to make more of them? So nutrients that we're going to be talking about are nitrogen, phosphorus, and iron, which are the main nutrients needed in an ocean environment. Now, in the northern areas of the planet, so like the polar ice caps and stuff like that, because they get continuous darkness for 3 months in the winter and 3 months of continuous daylight in the summer, their productivity is based on seasons. Okay, so in the winter they have very little productivity, which then starts to rise when you start getting sun. During May, it peaks. Okay, and then, or sorry, here, May, it peaks because there's a lot of sunlight, and it basically stays that way from June to October when you start to see the winter start again. So pretty much phytoplankton in the polar regions are only active when the sun's around. Okay. Now, density and temperature change very little with the depth in polar regions. Okay, and the surface and the deep waters mixing and all that kind of stuff. Remember, we talked about that. So melting ice during the summer creates what we call a thin, low salinity layer. And that layer doesn't mix well with deeper waters. And because it doesn't mix, the phytoplankton don't move to deeper waters. Okay, they get to stay on the top. And that allows them to produce continuously. And because there's, like solar energy limits, that limits the productivity in those areas. So in the polar regions, the lack of sunlight, sunlight is kind of the determining factor of how much productivity we can get in those areas. Now, in tropical areas, there's actually a low productivity because there's a permanent thermocline that prevents mixing between the surface waters and the deeper waters. And those deeper waters actually have all the nutrients, the nitrogen, phosphorus, and the iron. And so because there's a thermocline, two of them don't mix. And because of that, the productivity is limited by nutrients, not by lack of sunlight. Now, in temperate oceans, so this is like oceans like near Los Angeles and stuff like that, productivity is limited by both the sunlight and the nutrient supply. During the winter, there's very low solar energy. So even though there are a lot of nutrients, there's not a lot of productivity because of the photosynthesis, because there's not enough sunlight to do the job. In spring, you start getting more sun, which means more photosynthesis. And at the same time, we start developing a seasonal thermocline because of the hot and warm water. And that traps the algae in the light zone, but so they can be like really productive at first, but then they quickly run out of nutrients. Okay, so essentially, like in this picture, during winter, there's very little sunlight, not a lot is absorbed, and you have a lot of nutrients, but not a lot of productivity because not a lot of light. Then in the spring, you have increased productivity because there's more sunlight and they have nutrients, but they use those up really quickly. Now, in the summer, there's a very strong thermocline, which prevents more nutrients from getting in. And so, even though there's a lot of sunlight, there's low productivity because there's not enough nutrients. And in the fall, we again see that kind of still more productivity because there's sunlight and this thermocline is weakening, so more nutrients can get in until we get back to winter. Okay, so again, summer, lots of sunlight, but that strong thermocline prevents nutrients from getting up to that area. And then in the fall, because the thermocline is breaking down, we get more nutrients rising to the surface, but sun becomes a limiting factor again. So out of these organisms, right, you've got producers, which are organisms that make their own food, so things like phytoplankton and algae, and the organisms that eat them gain a small percent of their energy. Okay, now each stage of a food chain is called a trophic level. Okay, so going from algae, passing energy to zooplankton, passing energy to fish, and then to sharks. The transfer of energy is really inefficient. Okay, only about 1 to 2% of energy moves up to the next level. Okay, so for every 500,000 units received, for example, of sunlight, you basically have the phytoplankton. They make about 10,000 units of radiant energy is converted to this biomass. Then 1,000 units go to this one, to trophic level 2, to zooplankton. Then 100 units become available to the guppies here. Then 10 units become available to the tuna. And then, humans or sharks get to eat them and they get 1 unit. Okay. So basically, you lose like 99% of the energy as we move up the food chain. Now, a food chain passes along from one organism to the next. So this is a food chain on the left. A food web is where you have all of the different organisms and all the things that they eat and how they all connect to each other. Okay, so food chains typically go from producer to herbivores to carnivores. Okay, and the chain ends with the top carnivore, which is an organism that isn't preyed on by another organism. So like a shark. Okay, the food web is complex. Okay, it shows all the organisms they eat and their environment and all that kind of interactions and stuff. Now, food webs, if you have an organism that's connected in a lot of different ways to a lot of other organisms, they are more likely to survive catastrophe because if one gets nixed, then there's something else that could take its place. They have a lot of food sources in case one disappears. But there's some organisms that only eat one thing, and if that thing goes away, then the entire chain falls apart. Okay. And I believe that is it. Okay. So we're going to go ahead and do an activity today. So go ahead and move on to the next Google Classroom assignment. Thanks, guys.